in a previous episode, just to remind us, we went through some different principles for how one might try to take into account indexical information and saw some arguments for and against these. Today I want to first say something more about this issue of the reference class problem that we encountered last talk, and then move on to the ways that these principles can be applied. So you remember this slide from last time, where if you accept the self-sampling assumption, but not the self-indication assumption, you get this dependence on how you define a reference class, depending on whether that thing in the second picture counts as an observer in your reference class or not. You get a different probability according to the self-sampling assumption. The self-indication assumption avoids that dependence on the reference class. Nevertheless, the self-indication assumption had other issues, particularly with the presumptuous philosopher thought experiment. If we set aside the self-indication assumption for the time being, let's look a little bit more at how problematic this reference class dependence is. We can make an interesting observation, which is that different applications of anthropic reasoning will differ in the degree to which the result depends very sensitively on how you define the reference class. Let us consider this one. So here we imagine we have two big world theories. Remember, these are theories that postulate that the world is so big and diverse that all possible observations that could be made is made by somebody somewhere. And we then had this problem of how you can test such theories. So we imagine here that we have two such theories, the green theory and the red theory. They are kind of similar in all other respects, except they differ in the value they predict for this particular parameter, the mass of some particle. Let's imagine that everything else is constant. The total number of observers is constant. But they do imply that the actual value is different for this. Now, if we think about the distribution of different types of observations that will be made in this big world, these two different theories make different predictions about that. If the actual value of this physical parameter is 125, then most observers will observe a value of approximately 125. A few observers might observe all kinds of other values, either because this value is somehow like a statistical average, which might fluctuate a little bit over space-time. If it's like a thermodynamic quantity, you could imagine that there would be local fluctuations. Or maybe because some observers are have visual illusions when they're reading the measurement instruments, or for other factors. So according to both these theories, all possible values of this parameter will be observed, but the theory that says that the true value is 125 will postulate that there will be a peak of observations around that value. And this rival theory, the red theory, will say that there is a peak around 135, which it claims is the true value. So they are distinct in that respect. Now, intuitively, if we make an observation of 125, we want to say that this is evidence in favor of the green theory. And now we can ask ourselves, what assumptions must we make about the reference class in order to get this intuitively correct answer? So we can plot some possible definitions of the reference class there, like how. So we assume that we ourselves, if this is our observation, we must be in our reference class, and then some other set of entities as well. In particular, say observations or observers or observer moments that are sufficiently similar to our own should be in our reference class, and we can then ask how similar. Now, in order to make this reasoning go through to get the answer that we want, namely that green theory is supported by our evidence, it turns out it doesn't really matter very much exactly how we define the reference class, whether we choose the narrower reference class there or the wider one. This peak is sufficiently sharp that the answer will be the same in either case. There is vastly more sort of green than red under this particular curve there. So we get, and in reality, this would be much more sharply peaked, and it would be in a multi-dimensional space. There are many other things to your observation than this particular number, and you would get an extremely sharp focus of observations around sort of the actual properties of reality, as opposed to the ones that observers having illusions might believe there exist. Nevertheless, there is a limit to how narrow we can make the reference class. So suppose you took the limiting case where we included only observer moments that are subjectively indistinguishable from your own. So you're making this observation of 125, and we include only observer moments that are exactly identical to this. And such will exist according to both these theories. According to the red theory, there will be that many of them, and according to the green theory, there will be that many of them. But notice that if this is the reference class, then according to both red theory and green theory, all observation moments in your reference class will make your observation. So there is no difference. If you apply the self-sampling assumption, and with this as your reference class definition, then both green theory and red theory will imply with probability 1 that you should expect to see the value 125, because that's what all observers in your reference class see. So this would be too narrow a reference class. You need to get this kind of application to work, include a little bit more than just the subjectively indistinguishable observer moments. But as long as you include at least a little bit more, it doesn't really matter whether you include a lot more or just a little more, exactly how you do the extension. And we can contrast this with some of the more philosophical and paradoxical applications we encountered in the last talk, with the doomsday argument, for example. There, you have to make a much stronger assumption about the reference class. If there are going to be people in the future living hundreds of years from now or thousands of years from now, presumably they are going to be relatively more different from us. They're not just going to differ in sort of one pixel in their visual field, but they're going to maybe live very different lives. They're certainly going to know that they live at a much later time. They're going to ask different questions. They're going to know different things. Maybe they will even be some kind of post-human by then if they have used technology to change human nature. So to get the doomsday argument to work in a strong way, we've got to make a fairly bold assumption about the reference class, that it includes these very different kind of folk that would exist in the future if we don't go extinct soon. And the same for this Adam and Eve experiment. Like these two people, Adam and Eve, they are very, very special in the whole scheme of things. Only they will really wonder why they are the first two. They are in a very different epistemic situation, very different in many other ways from all the people who would come later. Now, maybe the reference class should be inclusive enough to embrace all of these, but that's a bolder assumption. And it seems that there is some correlation here between the degree to which an application is insensitive to the precise definition of a reference class and how, in an intuitive sense, how scientifically solid, robust, legitimate that application is, which is interesting. So the greater the sensitivity of the reference class, the shakier the inference seems to be. Perhaps one can see this as mirroring a similar feature. So the reference class definition in some sense defines a prior over indexical facts. Just as if you ignore indexical facts, you have from a Bayesian perspective some prior over different possible worlds that could exist. Maybe simpler worlds have a higher prior probability. Now, some Bayesians think that there might be a range of priors that a reasonable observer could have. And that there is no kind of simple logical argument that could pick out one prior as the only correct one. Nevertheless, you have to make some assumptions on the prior if you're ever going to get, say, ordinary scientific inferences to work. You've got to have a prior that somehow rewards simpler worlds so that the principle of induction can work. But a good scientific inference is one that for a wide range of different reasonable priors still gives you roughly the same answer. The evidence is so overwhelming that no matter exactly where you start from, you still are led to draw the same conclusion. And maybe what we find here is a similar kind of situation with regard to the indexical part of our prior. That the good inferences that use Anthropics are such that kind of lead many different priors to the same conclusion, even though not all possible priors. So now let's leap into some applications here. Cosmological fine tuning is, I think, the original application, and I will not say very much about that because our other speakers are talking at more length about that. To boil it down to its simplest, I think the idea is that there are certain physical parameters that seem as if they were fine-tuned in the sense that if they had been very different, no observers would have existed, nor life, nor perhaps planets, So that seems kind of puzzling, something that ideally we would want an explanation for. One possible explanation is that the universe was designed. So some theologians, notably Richard Swinburne here at Oxford, has used this fine-tuning argument to support the existence of a God who might have had a plan. He wanted a world of a certain kind. Maybe it's a good world. He was good, therefore he tried to design a good world. He picked the values. And that could theoretically explain fine-tuning, assuming there's no other problems with that kind of explanation. We would obviously have to look at that. But it's like one conceivable type of explanatory move one could make. Another would be if one could find a theory that eliminates this apparent fine-tuning, maybe some deeper, super-duper symmetry that makes all these things fall into place, so that from a few very simple postulates, you nevertheless show that the parameter had to have exactly that value. That's very nice. If one can get that, that would help explain it. It just seemed hard, actually, to find such a theory. A third alternative are these explanations that are called multiverse explanations. So you might think that there is an ensemble of different universes, which could be patches of one big space-time or disconnected space-times or different mathematical possibilities, each of which is instantiated. And if the value of this parameter varies across this ensemble, perhaps in some random way, and if the ensemble is big enough, then you would expect somewhere in the ensemble there to have been a universe, just by the law of large numbers, where the conditions are right for the existence of observers. And by then invoking this kind of anthropic principle, this observation selection effect, that kind of theory then predicts that we should find ourselves in precisely one of those universes where the conditions were right. And the fine-tuning is merely apparent. Well, it's true that our local part is fine-tuned for life, but the totality of physical existence is not itself fine-tuned. So the theory doesn't have to be fine-tuned. So those are basically the three possibilities. The fourth would be that it would just be a brute chance, that there would be no explanation, but that I think would be very unlikely to the extent that the fine-tuning is real in this relevant sense. And so that's roughly how this cosmological fine-tuning argument goes. Then like one can then delve into the details there, which are interesting as to how strong is the evidence that there actually is fine-tuning of this type. How sensitively does the existence of life depend on these various parameter values? And what is the evidence we might have for or against multiverse theories? And would those multiverses be big enough and varied enough to actually deliver the requisite diversity to then make the observation selection effect pick out the right subset? I think that all those questions there are legitimate, and attempts that have been made by some, maybe they are fading now because it's clear that a lot of cosmologists are taking them seriously, but there's still, I think, a strand of skepticism, at least small in others. But I think that there is at least a large segment of the researchers who recognize that there are real questions here and that they are non-trivial to answer. Now I'm going to go on to some, maybe a few of these will be less well known to the audience, but let's begin with the following two, which involve questions of evolution. First, the Fermi paradox, which you've probably all heard about. Like Enrico Fermi just wondered why it is that the sky seems empty, why we haven't seen any aliens. We know that there are a lot of stars out there, and now we know that there are a lot of planets as well. Billions and billions and billions, and yet no sign of any extraterrestrial civilization. They've neither come knocking at our doors, nor have we detected any radio transmissions or seen any other signs. So that seems kind of puzzling. Now, one obvious answer to this is that it's just very difficult to evolve life or intelligent life that would be visible from a large cosmic distance. And so even though you have all these different planets, if the probability for any one of them is sufficiently small, you would still expect to see no other life in the part of the universe that we have checked out, maybe in all of the observable universe. And to my mind, even though it's a very boring explanation, it is still perhaps the most probable explanation. And I suspect some people might be reluctant just because it is a boring. It's more fun to concoct like a more kind of intricate hypothesis where there are killer robots that keep a lookout for other civilizations that would want to expand into the cosmos and strike them down before they are. And there are like maybe 50 different explanations for the Fermi paradox that have been proposed. But to my mind, the simpler one is still active. Well, so this still seems maybe perhaps unsatisfactory in as much as it requires us to postulate that the evolution of intelligent life, that is us, was extremely improbable. And why should we, like a theory that implies something improbable, isn't that the theory we have reason to reject if there are better alternatives? Well, so here again the observation selection effect comes in. We have to assume that the universe is large enough that even though the probability for any given planet is extremely small, there are still enough planets in total that the theory implies it was very likely that life would arise at least somewhere. So this explanation requires that we have a theory that implies the universe is large enough. Unless you accept the self-indication assumption, in which case you expect a large enough universe anyway, just from the assumption itself. But as long as you have a big enough universe, which we seem to do, like all current cosmological theories suggest that the universe is really big, a lot of planets, then we can explain the absence of any sighting of extraterrestrial life just by saying maybe it's extremely improbable. Now, Brandon Carter had, and this is like maybe sort of the first couple of applications here, maybe the first sort of non-trivial ones, depending on what your notion of triviality is. But so he noted is that there is a kind of a cutoff for how long it can take for life to develop on a planet like Earth. There is a sun, and that remains for a certain period of time in its main sequence. In our case, maybe 10 billion years. We are roughly halfway through that when life developed. And this is kind of interesting. So if you think of each planet as having, like life tries to, like different chemicals bump into one another, maybe the right things have to come together in the right combinations several times. It's very improbable, but it's like a stochastic process. And there's an expectation time for how long this random process takes to generate something like intelligent life, or the precursors that can then evolve. And Carter suggested that our prior over how long this expectation time is should be very smeared out, because we really have no particular good insights into exactly how hard it would be to evolve observers. So if we measure this in some natural units, it doesn't really matter if you have Planck units. You could make the same with years if you prefer. But even the order of magnitude, we have very little idea about a priori. Like, does it take sort of on average a million years to evolve intelligent observers, or a trillion years? You could easily imagine different sort of chemistries that would make each of these true. So the prior probability would be smeared out over a very wide range of different orders of magnitude for the expectation time of life evolving on a given Earth-like planet. Now, since we know that on our planet it took about 4.5 billion years, we can rule out all those expectation times that are much shorter than that. If it usually happened after 1 million years, it would be very surprising that it took 4.5 billion years on our planet. We would have expected our planet to be, somewhat typical, maybe 1 million years, maybe 500,000, maybe 2 million years, but certainly not thousands of times longer. So we can, from observation, rule out this whole range. So that leaves two possibilities. Either it's just about this range here, or it's somewhere in this wide range that we haven't ruled out by observation. And Carter's point was simply that if we have a smeared out prior, and we chop off this whole part here, then almost all the remaining probability will be here, rather than in this narrow interval somewhere around here. So what this means is that if the expectation time is not much shorter than the time it took here on Earth, then it's probably vastly longer. So this then connects again to the Fermi paradox, that a vastly longer expectation time corresponds to the hypothesis that life evolves very rarely. And he thinks that that's the reasonable inference to draw. Now, this number of hard steps, so this is much more sort of speculative and problematic in its empirical assumptions, but it's nevertheless interesting. And a lot of applications of anthropics are like this, that the kind of empirical material you need to really make the inference engine works is, it's hard to get the right data. But they're nevertheless interesting, partly because they illustrate how something that seems like pure thinking or philosophy can nevertheless, at least in principle, be tested or lead to observational consequences, which is interesting in its own right. And also because the questions that these applications address are ones of great interest, that it's hard to get evidence any other way. So even if the inference is uncertain and it has to make kind of fairly strong assumptions to get on the way, it's nevertheless interesting because it's one of the few ways we have of getting any kind of grasp on these issues. So with this application, Carter imagined a model of evolution where it consists of a sequence of critical steps. So these would be independent steps, each of which is very improbable, and you have to sort of get through the first step, and then you get a shot at the next step, and you keep going until time runs out. So a metaphor for this would be maybe there is like a princess in a tower locked away, and then to get through to her, you have to pick some number of locks, and you have 1 hour to do this, and there might be, say, 5 locks, and these are like combination locks. So you just try them by random and error. If you get through the first lock, you then get to the second door where you get a chance to try the second lock. And the expectation times for these locks, like the number of combinations you can pick, might be very high. So if you have one suitor, he almost fails at the first lock, doesn't get through. But if you have a sufficiently long number of suitors lined up outside the tower, then eventually somebody will be lucky enough to make it through within the allotted hour. And we can then ask ourselves, what does the princess expect to observe? So she will like see some suitor making it through, and one can then ask, like, how long did the different locks take to pick for that suitor who made it through? And what we find here is that if the expectation time for one of these locks is very short, like if you usually just have to try like 10 combinations, so the expectation time is maybe a minute, then on the successful run, you expect that to have taken a very short time. It took like a minute to get through that lock. But once the expected pick time gets very high compared to the allotted hour, then the actual time it took ceases to give information. So whether it's like expected to take a year to pick a lock, or 10 years, or a billion years, you would still expect it to happen within, depending on how many locks you have. If there are 5 locks, you might expect it to take like 10, 20 minutes or something like that. And you can't really discern these different extreme levels of improbability just by looking at the time it took, because it's all conditioned on succeeding within an hour. So again, connecting this to the earlier observation that there is some time left over between when intelligent observers like us did evolve and how late they could have evolved, we can now get some information related to the number of improbable steps here. So if you're unsure about how many of these locks there are, and then you can observe how much time is left over when the suitor finally makes it through. You can draw some inference, namely that the more locks, the more really hard steps are, the closer to the total hour you would expect to have been used up. So if there are like 100 locks, the first successful suitor will probably have used up like 59 minutes of the total time. But if there's only one lock, then maybe 30 minutes, maybe 40 minutes, maybe 20 minutes, but probably not 59 minutes. So there is this relationship which you can mathematically calculate or compute between the time left over and the total number of these improbable steps. And then you can run this either way. If you knew the number of steps, you could calculate the expected time left over. So when Carter was running this, he thought that there was maybe 5 billion years left over, that we were roughly halfway through our sun's main sequence, and that was the cutoff for how long it could take. So he reasoned that there were only a very small number of these critical steps, 2 maybe, maybe 1, maybe 3, but certainly not 10, 15. Now, more recently, it looks like we have evidence suggesting that the Earth will become uninhabitable in maybe 1 billion years from now. So that would allow for a larger number of steps, make it less probable that it's only 2, maybe suggest more like 5, and so. So it's interesting that you can make these inferences at all. Now, in reality, there are a number of assumptions baked in here, particularly that you can model evolution as a sequence of improbable steps. there might be other steps that just involve a large lag. For instance, the evolution of aerobic metabolism. For oxygen breathing to become adaptable, there first had to be oxygen. And that took a long time to build up. There were these immense oxygen sinks, like iron and stuff, just lying about, that first had to be saturated by the oxygen pumped out by, or generated by earlier processes in organisms. And that took maybe 1 billion years. So it's not that this was very improbable, even though it took 1 billion years, but it just took a long time. So if you actually wanted to get specific numbers, you would want preferably a more detailed model of the evolutionary processes. Let's move on to another one where I think we can get a sort of firmer result. So you remember a few years ago when the LHC was being built, that there were concerns in the popular media about whether it could destroy the world by, there were different scenarios. A vacuum decay was one, or maybe a strangelet or a mini black hole or something like that. And serious note that there were actually some people who tried to some physicists who tried to run some calculations to try to put some bound on this. Sensibly enough, since even if the probability is small, as every sensible person agreed, there's the question of just how small does it have to be for it to be worth risking the planet. Now, so the kind of result that was computed is that we have these cosmic rays bombarding the Earth all the time. Some of these are very highly energetic, more energetic, in fact, than the collisions we expected in the LHC. So if we assume that there is some kind of equivalence, there's no relevant physical difference between the high energy events in our particles and the ones that occur naturally, then by just looking at how frequently these occur naturally, you could put a bound on how dangerous our accelerator could be, and it's very, very reassuring bound. One thing that this kind of calculation does not tell us, though, is how dangerous are these things that occur in nature. Like, even if we assume that our accelerator generated events are equivalent in all relevant, including potentially unknown physical respects, if you think about how would we actually know how frequently, as I say, focus on the case of the vacuum decay, which is the easiest to see. Now, if there were to be a vacuum decay somewhere, it would spread at the speed of light and destroy everything in its path. So if it happened over there, you wouldn't see it coming. If it had happened 1 million years ago, 1 million light years away, the time when it arrived would also be the time when you were destroyed. So no observer can sort of see themselves suffering a vacuum decay. They are unobservable. And so this might lead us to wonder, like, we think they are rare because we've never seen a single one of them. But then it seems, if you think about it, that whether they were frequent or rare, nobody would still ever have seen any of them. So how can we really place any bound on this at all? Like, suppose they happened like once every 10,000 years in a volume like the solar system or something like that. Or once every trillion years, or once every trillion years, or never. Like, how can we distinguish these from observation? So we thought of one way of doing this was by looking at the birth dates of our planet. So if the vacuum decays were very frequent, then increasing portions of the cosmos would be sterilized. There would be these bubbles growing. And if these happen very frequently, then almost all planets would be destroyed early on, and there would be an exponentially declining population of planets as time went by. And most observers that would form, there would be many fewer of them in total because planets would get destroyed so early, but most of the ones that did arise would happen on planets that were born exceptionally early, before large tracts of the universe had been destroyed. Now, we know something about the distribution of planets in the universe, including Earth-like planets with the right metallicity and so forth. And we know that the Earth is not particularly atypical in this distribution. Earth is not an extremely early planet. And so from this, it's possible to put a bound on how frequent these kind of vacuum decays could be. And by just using standardly available data, we could put a bound on the risk of annihilation of 1 in a billion years with a 99.9% confidence level. The true risk might be much lower, or it might be that this never happens, but one can easily get a bound of roughly that magnitude. So you can see that the shorter the decay time, like the more frequently these vacuum disasters happen, the more left skewed the distribution of planet formation dates would be, because most of it would be gone after a short period of time. Let's look at this anthropic shadow thing. So this is kind of slightly related. We get a similar problem with observation for a number of other events that might not be as certainly deadly as standing in the way of vacuum decay, but that might nevertheless carry some risk of extinction. So imagine like asteroids hitting the Earth, or supervolcanic eruptions, or other supernova, or other events like that. They might come on a spectrum of severity, but as we go up the spectrum, say larger and larger asteroid impact sizes, a real risk arises that they will extinguish some subset of the life that exists on the planet. A sufficiently large asteroid might kind of eliminate all higher life, and a smaller one might knock off human-like precursors. So we can think of some underlying distribution that has some probability or some frequency with which a given type of event occurs. And then if that type of event occurs, there is a certain probability that it leads to extinction, and some other one minus that it doesn't lead to extinction. And the larger this probability that it leads to extinction, the greater the degree to which it would be filtered out from the evidence that we can have about these. So to draw correct inferences from the historical record, we need to correct this sort of observed distribution of crater impacts or events that we see in the past, and check whether they would influence the number of observers that would be expected to exist later. And if they do influence that, we need to correct for that, and then we can derive a better estimate of the underlying probability that generated this observed distribution. And it's then that underlying probability distribution that we should use to derive predictions for like how much danger we face going forward. In other words, we have, it seems, a kind of anthropic shadow. So if we plot, say these are maybe asteroid impacts, and this is time. Here is the Earth is created here, and then we have now. This is schematically. We have, first of all, some traditional selection effect, not observation selection effect, just ordinary selection effect, that if we go very back in time, we can't see a very small impact because it will have been, the rocks will have been eroded. So normally we would expect to have, the further back in time, we can only see bigger events just because the evidence kind of gets erased. But then we also have this sort of anthropic compatibility boundary, like a really deadly event couldn't have happened very recently, or it would have wiped us out or wiped out our ancestors. If we go further back in time, maybe a larger impact could have happened and we would still have had some time to recover our evolutionary ancestors. And it's only in this intermediate region here that we have sort of unbiased data. So just for fun, we can look at the actual, these are crater diameter data. So again, the earlier point is like the data is kind of crummy and stuff like that. But you can to some extent see the classical selection effect. There is no really tiny crater observed from very long ago. Like there are a lot of those recently, but you can't see them when you go back billions of years. You also see this upper rectangle here kind of empty, as you would expect. If there had been something really big there, we wouldn't be here. Now, there could be other explanations for this, like maybe the population of impactors has just been depleted, stuff like that. But even if it weren't, we would still not expect to see anything up there. This guy here is kind of an outlier. That's just the guy who killed the dinosaurs. So that is a confirmed catastrophic, and that seems roughly maybe the boundary. Like if it had happened more recently, we probably wouldn't be here, or if it had been much more severe, we probably wouldn't have been there. So the simulation argument tries to show that one of three propositions is true. One of them is that almost all civilizations at our stage of technological development go extinct before they reach technological maturity. They find that having developed all those basic technological capabilities that we already have reason to think are physically feasible eventually to obtain. The second possibility is that there is a very strong convergence among all technologically mature civilizations, in that they all, or virtually all of them, lose interest in creating what I call ancestor simulations. That is, detailed computer simulations of people like their forebears, detailed enough, maybe to the point where you simulate the neurons in the brains of people who lived before, detailed enough that these simulated people would be conscious. So at the moment, it seems a lot of people are curious in doing this. We run all kind of games and stuff like that, and scientific simulations, and if we could, we'd probably run more of them. But maybe there's a very strong convergence where all advanced civilizations just completely lose interest in doing this. And the third possibility is that we are almost certainly living in a computer simulation. In a literal sense, not that we can describe the universe as if it were like digital, but that it's inside a computer built by some advanced civilization. So how does one get this strange result? Well, one can make estimates of the amount of computational power that would be available to a technologically mature civilization. So there are all kind of computational systems that we can't manufacture, but we can model them. And we can see what kind of performance they would have, and we can see how that performance would scale if we just made bigger systems or more of them. And the short story there is that a mature civilization could have astronomical amounts of computational power. You can also estimate how much it would require to run one of these ancestor simulations. You first have to figure out how much a particular human brain requires, then sort of scale that by the number of brains and the duration that you want to simulate them for, and add in some for the environment. And even if you make very conservative assumptions on both of these estimates, which are quite uncertain, there's still such a big gap between them that you still find that by using only a tiny, tiny fraction of its computational resources for this purpose, a technologically mature civilization could, during its career, which might last for billions of years, it could run billions and billions of ancestor simulations, even by just using a tiny fraction of 1% of its resources for this purpose. So then you can simply write down the formula, the fraction of people like us who live in simulations compared to the fraction of people like us who don't live in simulations. And you can see it without going through the mathematics there, if you just think about it. So you have these three possibilities. Like, suppose the first one was false. So some non-trivial fraction of civilizations like ours do reach technological maturity. Then suppose possibility 2 was also false. So non-negligible fraction of those use some of the resources, some non-negligible fraction of the resources to create simulations. Then because that would result in an astronomical number of simulations, there would be many, many more simulated people like us than there would have been in the original segment of history. So if the first two possibilities are false, then most people with our types of experiences would be simulated. And then by the self-sampling assumption, we would probably be simulated. In fact, for this particular purpose, you need something weaker than the self-sampling assumption. You don't need to resort to the full strength of that. You only need to resort to what I call the bland principle of indifference. So here, you only need to think of yourself as a random sample within a class of observers that you have no way of telling which one you are. So it's a particularly weak version of it. And so then if you reject the first two possibilities, you get the third one. So you can't reject all three, so at least one of them is true. And that's the simulation argument. And there is there's one common misconception, which is that to run a simulation, you would somehow have to figure out how computationally intensive basic physics is. Like how much computational resources would it take to run the Schrödinger equation for the universe or something like that, and then imagine it's. But so that's not the idea at all. The idea is that you would have to run a simulation that is, from the point of view of an observer in that simulation, indistinguishable to the outside world, or at least close enough that they couldn't tell. And that's a vastly more relaxed requirement. I mean, I have no idea of knowing what happens inside this podium right now, whether all the molecules and atoms are wiggling in exactly the right way that physics prescribes. You could just, eliminate all of that from a simulation. Now, if I put an electron microscope to this table, maybe I could see more, but then the simulation could fill in detail on an as-needed basis. And similarly, remote astronomical bodies and stuff, all of that could just be radically simplified. And the real bandwidth here seems to be sort of the human brain's ability. There's only so many sensory signals going in, and that kind of puts a cap on how complex the simulation could be. Anyway, let me stop there and take some questions.